Now what? Let's think about the excited state of aldehyde case. So as I already mentioned in the photochemistry, component molecules are one of the key players in photochemistry, and the excited state of carbonyl is quite important. So let's think about the simplest case of carbonyl, which is form aldehyde case. So first, I would like to mention that we are going to draw the energy diagram before thinking about the excited state, of course. So we have to understand the ground state before going into the excited state. To draw the energy diagram, you have to keep in mind that this case. Now we are thinking about the two different types of atoms, both carbon and oxygen. And when we think about the different type of the atoms, the atomic orbitals, the energy of atomic orbitals compared to for the same type of the atomic orbitals, the energy level is lower for the larger atomic number atoms. So just keep in mind this, and also you have to keep in mind, and in the case of she-O bond, in this case, I'll just mention that this carbon is sp2 orbital, and then again this oxygen side is sp orbitals. And again, I would like to remind you that this oxygen can have several different types of orbitals, but for simplicity here, I would just assume this one has sp orbital. Okay, and also I would like to mention that in the case of oxygen has non-bonding orbitals in one of the sp orbital, and also py orbital. Y is just taken this way. So just keep in mind this. Please stop the video and then draw the energy diagram and how to make the bonding orbitals for CO. Okay, then let's think about this. So take the energy, and first we have to decide what kind of atomic orbitals are involved in for making bond. And on the side of the carbon side, then we have one is sp2 orbital, as I mentioned, and then pz orbital. So each one of the orbital has one electron. And this is a carbon side. And oxygen side has sp orbitals, and also pz orbitals are involved. But compared with the energy level for carbon and oxygen, they are lower than the carbon side, right? And this one is sp, and this one is pz, because and sp orbital is more, the ratio of s is larger, so it's further lower. And each one of them has one of the electrons. And also, as I mentioned, there are in the case of oxygen has actually another orbitals of this one's py, and then this one is sp. But as I mentioned, these orbitals are already kind of occupied by the electrons of oxygen. And by making a bond, sp2 and sp are making the sigma bond, which is like this. And in the case of pi orbitals, the overlap is smaller, so it's like this. So this one is sigma, and this one pi, this one pi star, this one sigma star. And then each one of the electrons are coming to making a bond in like this. So the thing is, in the CO bond, the two of electrons are occupy the sigma bond and a pi bond, but one of the important things is this one. The difference from the ethylene is these two orbitals are occupied, but they are related to the excited state. It's an orbital. So just drawing this energy diagram, we can learn several things. And one of the things is in a ground state. In the ground state, the electron energy for bonding is close to the oxygen electron side. So meaning that the bond is in the bond, the electrons are more close to the oxygen side. So meaning the oxygen is in a ground state is polarized, negatively, more negatively charged. So what it means is you can see that the pi, even for pi bond and the sigma bond, this energy level is close to the energy level of oxygen side, right, compared with the orbitals in the carbon side. So these the pi bond and the sigma bond is more likely similar to the oxygen side orbitals. That's why, as we know that in the case of CO bond, the oxygen side is negatively charged because from the high school knowledge, it's due to the electron negativity. It's larger in the case of oxygen. That's why the oxygen is negatively charged, but it can be explained from the consideration of energy level too. But now what? When we think about if the light is illuminated and one of the electrons is excited to the anti-bonding orbitals, in the anti-bonding orbitals, this electron is now more similar to the original orbital of carbon. So in the excited state, on the other hand, is quite similar to the orbital feature of the carbon side. So the ground state and excited state is opposite. So as I mentioned, electron energy is close to when the one of the electron is excited. The excited electron is now resemble the original orbital of the carbon side. So it means that when the photoexcitation occurs, the character of the electron orbital, the electron feature is quite different, the opposite. So ground state, the electrons are originally similar to the oxygen side, but if once it is excited, it's similar as the original carbon orbital. And with that, we have different type of orbital: sigma, pi, sigma star, pi, pi star, and also non-bonding orbital. And in the case of carbonyl, you have many variations of excited state you can think about. One is sigma sigma star state, the other is a pi pi star state, and also this is this n pi star state, which is electron is excited from this side to this side, this to this. And actually, in terms of photochemistry, this state is one of the most important excited state, because just simply from this excited state, many photochemical reactions occur. And at this point, I'll just stress that you can imagine that the non-bonding orbitals are originally electrons are from all the electrons from oxygen side, and then they are localized as the oxygen side. But once it is excited, for example, in this case, n pi star state, this electron moves to the pi star state, which changes the electron configuration quite a lot, meaning that that's kind of the difference from the ground state to excited state, and huge difference of electron configuration. Originally, this is negatively charged at local position of oxygen to this electron spread around the CO bond. That makes the electron character, molecular character changed. That induces the chemical reaction.